Thanks, Emily. Hi, everyone. I'm Stefan. Today, Rick and I are going to talk about what we've been working on for the past few months. Essentially, this is a software package called PyLabRobot, which provides a universal model and hardware-agnostic interface to liquid handling robots. Just so everyone knows, we'll be recording this presentation and uploading it to the internet. So if you ask a question during the presentation, it might go online. This is just a quick outline because Rick and I are going to be switching off who's presenting. So this just kind of explains what the sequence of events is so you can kind of know what's coming next. All right, I will now cover some background of the problems we've tried to address with this software package. So one of the most interesting aspects of living systems is that they're often made of modular components. By modular, I mean, it's a piece of a system that you can characterize the inputs and outputs of in terms of behavior and place that piece in a new context and expect it to still follow the same rules. This is an extremely useful aspect of systems for designing complex systems because you can create arbitrarily complex systems that follow well-defined rules by composing them of well-defined modules. Composition allows us to abstract away from details, which can facilitate comprehension. Arbitrary levels of complexity can be achieved by composing modules that are each composed of their own submodules, and so on. This is very much the case in living systems, where we see a great amount of diversity arise from the combination of a small number of different parts. This is efficient from an evolutionary perspective, because components can be repurposed from existing systems to create new functionality. The modular components that are illustrated here are whole cells on the left-hand side, elements of genetic circuits in the middle, and components of signaling pathways on the right-hand side. Steps in biology protocols are also modular and composable. So most steps in biology protocols follow just one of a small number of different unit operations. We have centrifugation, incubation, vortexing, and of course, aspirating and dispensing liquids across different containers. If we can increase the scale or efficiency at which we perform these unit operations, then we can increase the rate of discovery across many fields of biology. It's good that we only need so few unit operations because biology is a very labor-intensive field of science. Biology is too complicated for us to make big predictions on the basis of theoretical models like in physics, and even minor discoveries require extensive experimental work. There's little opportunity to advance on the basis of theoretical insights alone. Because of this, great projects in biology are often undertaken at an institutional scale. Experimental work must be planned and coordinated across many collaborators in order to achieve the scale needed to make significant progress. Data collected on this scale must be aggregated into a framework that streamlines analysis. Modern biological research has taken on an industrial characteristic due to the degree of coordination needed across many contributors. Industrial processes often also benefit from the use of modular and composable workflows. Because we depend on the accumulation of a large amount of data to validate findings, there's a close association between the amount of time spent running experiments and the speed at which new discoveries are made. Here are a few examples of landmark projects in biology that depended on the work of hundreds of collaborators. I'll highlight that these are not just top-down, hierarchically coordinated projects, but also frameworks for organizing the results of distributed and dispersed contributors. The point of this is that biology is a very labor-intensive field, and we can drastically increase the rate of discovery by using robots that aspirate and dispense liquids. For labs using robots, the bottleneck for producing results is no longer how quickly a scientist can execute a protocol, but how quickly they can write a script that tells a robot how to do so. Once this program is written, it can be deployed across any number of robots to whatever scale is desired at a fraction of the operating costs of a human scientist. There's just one problem. It has historically been extremely challenging to program liquid handling robots. They are shipped with inflexible proprietary graphical user interfaces that do not resemble a modern programming environment. They do not integrate easily with external hardware and software, and they do not give the developer freedom to create their own tools and abstractions. In short, the software for these robots do not fit as modular pieces into a larger organizational framework. PyHamilton was first created to address these challenges presented by the proprietary robot graphical user interface. It was the first ever example of a truly modern programming interface to liquid handling robots. PyHamilton scripts are just Python scripts, which is extremely advantageous because Python allows us to build abstractions that package complex functionality into a simple interface. PyHamilton enables robotics programming to enter the highly productive ecosystem of modern software. PyHamilton has been extremely successful at addressing our own lab needs, and adoption in industry is accelerating exponentially. However, it has a crucial limitation that prevents full integration with open source ecosystems. PyHamilton relies on the proprietary Venus application, which runs only on Windows, as an intermediary communication layer to the robot. How do we create a fully open source interface? Rick and I started discussing a potential collaboration in January around creating a way to control Hamilton robots from a Linux environment. Starting in July, he joined the lab as a visiting student from the University of Leiden in the Netherlands. I'm going to hand it off to Rick now to talk about what we created to address the problems I just discussed.
All right. Hello, everybody. I'm Rick. Today, I'm going to talk about PyLabRobot, which is an open source pure Python library to work with liquid handling robots. And we believe this addresses many of the barriers Stefan just described. In PyLabRobot, the unitary operations Stefan just mentioned are exposed as Python functions, which you can see in the 4 lines here. You can compose these to create any molecular biology protocol. You can also move plates on the Hamilton robot using iSwap, for which you can see the code on the left here. There's also a short video. Or you can just move the plate. You can also integrate with plate readers, which are now their own Python object, where you can move a plate from the plate carrier to a plate reader. In the future, we hope to have this plate reader object also expose a read plate function, where you can actually interface with this plate reader as a real plate reader instead of just the location. The wonderful thing about the code you just saw is that it works with any liquid handling robot, independent of which model. So it's hardware agnostic in this way. We are agnostic on 2 fronts. One is to the liquid handling robot. So that's what I just mentioned, that you don't care about the liquid handler you're running something on, but also agnostic to the controller computer. So for example, I can use my Mac and other people can use their Linux laptops to control the liquid handling robot instead of just being tied to Windows. The big idea here is that cookbooks only work because they are agnostic to the kitchen you run a recipe on. If a recipe were just tied to a particular kitchen, this would not work. And that is the case in biology or lab automation protocols today to a large extent. And we hope to have addressed this. So how are we agnostic to the robot? To build this, we introduced a high-level API called LH, or Liquid Handler, which just exposes the intense and high-level abstraction of what liquid handling means. So those would be unit operations of to pick up, discard, aspirate, and dispense. Liquid handlers are responsible for talking to a variety of different backends, which know how to talk to a particular robot. So we have a star backend, which talks to Hamilton robots. We have an OpenTrons backend that talks to the OpenTron robot. We also have a simulator backend, which makes sure you can use the same liquid handler API to simulate methods. And then in the future, we have planned support for Tikan robots as well. Besides liquid handlers, we plan to move to full lab agnosticism in the future by exposing similar APIs for plate readers. And this model is extensible, of course, to all kinds of different hardware. Besides hardware-based backends, as I just briefly mentioned, we also have software-based backends. The most important of which is the simulator, which is an accessible way to train and explore liquid handling from the comfort of your own laptop without having to have access to a liquid handling robot or even having to install anything. This project is currently in alpha and requires an access code to sign up for, but we hope to release this to the public in the future. Alternatively, you can already run this locally, which is free for us and extremely scalable. Besides it, we have an interactive version planned. The current simulator only displays what's going on. We would love to have a way for people to interact with the simulator on the right-hand side here and control what's going on in the code too. The simulator is highly configurable using a menu of settings. And also the simulator is fully open source. So if there are features missing, you can just create them yourself, which is a very important benefit. Besides the simulator, we also provide an HTTP backend, which is a very standard internet protocol. And this will allow you to run an instance of Liquid Handler locally, which will then talk to HTTP, which sends network requests to any server. And this allows for full extensibility. We provided one implementation of such a server, which is called the OH server, which talks to OH, which then can talk to a robot. So you can imagine running this part locally and then having this part run somewhere else in the world. It should be noted that these are not dependent on each other. They're just compatible, but you could use anything on the left here and anything on the right, and it will still work. A very important part about being hardware agnostic or robot agnostic in particular is how do we manage resources, since resources are a little bit different for each robot. To do this, we have to carefully examine how resources are actually represented on the deck. We sort of view this model of resources as a tree where the deck is the root of the tree, which contains many child resources, if you will, which can be carriers, just the blue bucket, plate carriers, or a plate reader. And then for the tip carrier, for example, it contains tip racks, which you can see on the bottom here, or plates in the case of a plate carrier, as their respective children. And then if you want to know the location of any particular resource, we start with a resource, which you can see on the bottom here. And then we ask what its location is relative to its parent. So that is, for a tip rack would be the tip carrier and not the deck itself. And then for the tip rack, we ask, the tip carrier, we ask what its relation is to the deck itself, which you can sort of schematically see on the top right here. And this way, if you, for example, move a plate carrier, you only have to update a single line, and everything else will automatically be computed if you request it, which is extremely flexible and also allows for easy implementation. Just to dive a little bit into the code, since there are a lot of programmers around here, this is our resource class, which sort of defines a blueprint for instantiating objects of resources. We store the name, the size in all 3 dimensions. And in addition, we also store the parent of this resource, which in the case of the deck would be none, which means there's no parent resource. And then you also keep track of all the children that this resource may have. When you assign a child to a resource, you have to tell the resource that the parent is ourselves. So if I were a tip carrier and I would get a tip rack, I would tell the tip rack that I'm the parent, and then I would also store it on my children. And for unassigning, you basically do the reverse. The wonderful thing about having resources defined abstractly in Python like this is that you can actually define any resource as you like. So for example, the blue buckets are now their own Python resource, where they would previously be represented as just plates in Venus, which is not the best in our opinion. Don't worry, we also have access to all Venus resources. You don't suddenly lose the ability to import them. This is just a few of them. And there is an easy way to import other resources that we may not have implemented ourselves yet. One thing that's very neat about combining Venus resources with the resource class in Python is that you can do things like create a resource stack, which is a stack of multiple Venus resources. This is something that Bo showed me the other day, where you stack a plate on top of a lid for extra stability. And this you can now natively represent in PyLabRobot as stabilized wells, which I think is a good name. The second part about hardware agnosticism is that we are agnostic to the host computer. This means that you don't care if you're just running on the old Windows laptops, but you can actually use your own laptop. and just plug it in as you would use an external monitor. To understand how this works, we have to dive a little bit into how PyHamilton works. Keep in mind that this is immensely simplified and just represents the very, very big picture. There are many more steps in the actual PyHamilton. So to start on the left here, the computer or the user is what would talk to PyHamilton via the Python API that it exposes. And then PyHamilton in turn is going to talk to the Venus program, which unfortunately only runs on Windows. The Venus program then builds firmware commands, which it then sends to the robot over a USB cable. All right, so how PyLabRobot works is that instead of talking to PyHamilton and Venus, we talk to PyLabRobot, which itself knows how to create firmware commands. And since this is all in Python, you can run this part on any computer. And then it still sends the same firmware commands to the robot. For backwards compatibility, we also provide a way for PyLabRobot to actually talk to PyHamilton, which will then talk to Venus, which will then create firmware commands, which ensures that if you use PyLabRobot, you can still use PyHamilton for the part where we have not supported this line yet. We, of course, hope to capture this full path here eventually, and we are almost there already. All right, so now I have a live demo to show you. So just gonna move this here. All right, so this is the PyLabRobot platform, which is a hosted Jupyter notebook that we run in the cloud. We start by importing the liquid handler and the simulator backend. Then we create those and set them up. As soon as I set them up, you can see on the right here, the simulator appeared. Then to set up the deck, we import a couple of resources. And then as soon as I assign a resource, like a tip carrier, you can see it appear on the right here. On a real robot, you unfortunately cannot do this. You have to put in a resource yourself and then tell PyLabRobot where the resource is. Within the simulator, we add them when you call assign. Let's do the same for a plate carrier here. And then on a real robot, you would need to fill the tips in the tip rack and like put liquid in the wells. In the simulator, you cannot do this. So we provide these methods called fill tips and adjust well volume, which do what they sound like. You can see here that since we have alternating 100 and 800 microliters of volume, that the opacity of the wells will reflect the amount of liquid in a well as the visual cue. And then for the liquid handling protocol, we want to pick up a tip from tip 86, which, as you can see, takes a little while, just like it would in a real robot to sort of represent reality. You can turn this off if you are in a rush. Then we aspirate from the top right here. It's just 10 microliters, so it's not really visible, but we aspirate it. And then we dispense into the same well. And then finally, when we are done with this very simple protocol, we can put the tip back and you will see it reappear at the bottom here. All right, so when I have written this method in the cloud, I can actually go and download this notebook. And then on the OpenTron, for which I have a notebook here, I can upload this file, which we have just written. Click upload, open a notebook. And then there are, of course, a couple of things we need to change to go from the simulated environment to an actual robot. We can still use the same liquid handler API, but then instead of the simulator backend, we are going to use the OpenTron's backend. And then instead of instantiating a simulator backend, we will instantiate the OpenTron's backend. And then you can see where we pass backend equals the simulator backend here. We're going to pass the OpenTron's backend. I'm going to go setup, which takes a little while. Can move on to deck setup. We have to import a little bit different resources because we use a different layout on this deck. Now you can see that we import the Kerning CoStar plate here, which typically is a Hamilton plate, but it can also work with the OpenTrons. And this resource is defined as a Venus resource, which is really cool. And then instead of the carrier, we define the tips as the OpenTrons tips, and then use the same plate. And I'll assign the resources to the robot. The resources are in the robot. I just have to tell PyLabRobot that we have them. Oh, I already ran that code. All right, I'm gonna remove the simulator specific code, of course. But I can keep the liquid handling protocol, which is the most important part. So are you ready? All right. So in the hi, there's.
Oh, sorry. Could we see it?
I think
Do you want
not.
to move your computer over to the face it towards the
I
open
could
door?
actually hop on the Zoom from my phone.
Yeah, it's a great idea. Do that.
All right. In a second. Right. You could imagine in a real script something like a flag, like if simulate do X, else do Y. Just for the simplicity of running everything in a notebook and highlighting the differences, I haven't done this. But in a real script, you would like import a file that like sets up your simulator environment or something.
And an important point is that in this demonstration, it looks like it's a lot, but generally the liquid handling protocol itself is incredibly long, like thousands of lines of code. So this is really just the first couple of steps to initiate whether or not you're on the robot.
So
I think for the
picked up a tip, as y'all can see. And then we aspirate from the plate. We're just aspirating air here, but you can imagine this is liquid. And then we put the air back. And then when we are done, we also put the tip back. All right.
you want to switch back to screen sharing?
Yes. All right. So now we have run something on the OpenTron. But as many of you know, we also have Hamiltons in the other building, which we can also control. I have a live video feed here of the Hamiltons. I'm FaceTiming with the Hamiltons. And then here I'm gonna upload the same notebook we just wrote in the simulator. We can, again, import liquid handler. We have to do some things we just did. There's a little bit less of a reconfiguration since the simulator currently works best with the Hamiltons. In the future, we'll make the simulator work with OpenTrons to like provide a better integration. So just import star, which is the model of the Venus robot that we use, and then create a backend called star and pass it to the liquid handler, and then call setup, which displays some things. As for the deck setup, we can use the same deck setup we used in the simulator. This I have set up in advance. Remove these cells again, and then we can pick up a tip remotely, aspirate some air. And kindly put the air back again. And finally, discard the tip to the tip rack. All right, then concludes the demo. Just to recap what we just saw, we wrote a method online without having to have access to a robot or installing any software. Then we ran the same method on an OpenTrons robot using a mixture of resources defined by OpenTrons and Hamilton's Venus. And then run the same method remotely on the OpenTrons. All right, I'm gonna pass it back to Stefan, who's gonna talk about community and related projects.
So the point of all of this is not so much what it is, but what it allows you to build. And so I mentioned earlier that once you have access to this this productive ecosystem of modern software development, then you can build a lot more efficiently than with the proprietary GUIs. And so these are some sort of quick examples that each of which were created relatively quickly that kind of illustrate like the types of applications we want to demonstrate that you can create with the PyLabRobot framework that are basically impossible or extremely challenging to create in like an external tool. So I'll just kind of walk through here. Actually, don't want to pause that. So on the bottom left, we have the PyLabRobot terminal scheduler application. And this just provides like a simple terminal interface to either like kicking off robot scripts or adding time slots to calendars and like reserving and viewing other reserved time slots. So this is pretty valuable because robots are very expensive, oftentimes shared resources, and people want to kind of be able to plan their experiments in advance. So that's how we expect it to be used in our lab. On the top right, we have a really simple example of training a GPT-3 model to write a PyHamilton script. So the way that this was done is I gave GPT-3 a few examples of, this is a PyHamilton script that aspirates from these wells and dispenses to these wells. And then I gave it a script, and then I gave it a few more examples, and then I said, write me a PyHamilton script that does this. And the green highlighted text is GPT-3 writing, and it got it right. The bottom right, bottom right example is a basic kind of like controller application that we use to hook up a video game controller to the Hamilton robot. So basically we have the sort of atomic commands given by the PyLabRobot framework, and then we can call those commands from another sort of Python environment or Python library that is compatible with the game controller. And so all this took was hooking together two existing libraries of code in a pretty straightforward and simple way to create functionality that had, like, as far as I know, never been created or demonstrated in any capacity at all. And on top of this, there's, you know, many more applications that I don't have time to get into. For engaging with the community and sort of getting a sense of what's valued in the field of lab automation and just kind of bringing together people to share expertise and community resources around lab automation, we started hosting a forum at labautomation.io or forums.pylabrobot.org. That's just a basic like discourses forum that has gained a lot of activity among just professional lab automation engineers, scientists, business people who want to get a sense of like what's out there, or people who have their own really interesting ideas to contribute. And we've already personally obtained a ton of value from using this, because there's like Hamilton engineers who were providing like questions and answers to really like key questions that many, you know, we just didn't have the ability to get answered before this existed, and now they respond like within sometimes hours. And that's the case for many users in the forum community. Some of the coolest examples of projects that people have posted are these DIY projects by Jason Desrosiers, who is a engineer at PerkinElmer. I think he's an automation consultant at PerkinElmer. And he's created these masterpieces of like open source engineering. There's also job postings.
All right.
Oh, yeah.
You want to continue?
Oh, you go.
All right. So what's on our roadmap, or what's next? I want to support many other robots, such as the Decan, which is available here at MIT. Also, the open trons are currently a work in progress. Most things work, but there are a few things that we need to finish up on. In addition, we want to provide a model for asynchronicity, which means that we want to provide a more natural way to express the idea of doing through lab automation things at the same time, such as in parents, reading a plate and cleaning the tips. We also want to provide support for other types of equipment, such as plate readers, pumps, etc., to create a truly lab agnostic Python library. We want to open the simulator to the public, which, as I mentioned, is currently in alpha. Let me know if you want an access code. And we want to make the simulator interactive. Right. And then we want to thank Dana Gretton, Emma Curry, John Bloom, and of course, Gavin, and the entire Sculpting Evolution team